Good morning to one and all. I am Parthiban, working as assistant professor in the Department of ECE, Sri Muthukumaran Institute of Technology, Mangadu, Chennai. Now I am going to talk about the subject called satellite communication, which is coming under the regulation R 2021. The subject code is CEC 352. Now I am going to talk about Unit 3, which particularly deals about the satellite link design methodology. So what is this link design methodology, which is one of the most important engineering procedures in the satellite communication? So far we have studied about the satellite basics, uplink and downlink, as well as about the link budgets, as well as about the carrier to noise ratio, as well as about the GT ratio, as well as about the link margin. Now we are going to deal with the satellite link design, which involves the design parameters that is required for successful communication. So the design must have a required signal quality. It should have a required bit error rate. It should have a required availability. It should have minimum interference. It should be cost effective. It should be regulatory compliance one. So these are the factors that we are going to see. So first of all, the frequency band determination that plays a very crucial role, since that is the first step we have to follow the procedure for satellite link design methodology. The first step involves the frequency band determination, since the operating frequency is very crucial, since it directly affects the antenna size, atmospheric losses, bandwidth, equipment cost, as well as the regulatory requirements. Then coming on to the next step, that is called the satellite communication parameter determination, make informed for guesses for unknown values. That is also very important one. So there are some standard values are there that we can take into account. So which is a very important one for higher frequency, since a higher frequency selection involves more bandwidth, smaller antennas and more range attenuation. So lower frequency can be better for propagation, but it requires a large antennas also. So the satellite parameter definition involves or determination involves the satellite EIRP, the satellite gain, the satellite footprint. Footprint is nothing but the coverage area. These are the three prime factors, as well as the transponder bandwidth, as well as the satellite position also. So these three factors must be very important. Then coming on to the third step, which is going to determine the earth station power determination. So in the earth station power determination, both for uplink as well as the downlink, the antenna diameter is very important, as well as the antenna gain, as well as the transmitter power, as well as the receiver noise temperature, as well as the GT ratio. These are all very important in step 3 calculation. In the step 4, we are going to establish the uplink budget. So that involves the transponder noise power budget to find the CN for the uplink budget. So the objective is to determine the CN for uplink. That is very important. So which is based on the air station EIRP. EIRP is nothing but the equivalent isotropic radiated power that depends on the PT and GT. As I already told you, PT is nothing but the transmitter power, GT is nothing but the gain of the transmitter. The uplink free space loss also should be monitored, as well as the atmospheric loss should be monitored, the rain loss should be monitored, and the satellite receiver gain should also be monitored, and it should be measured carefully. So these are the four important aspects that we have to take into account while establishing the uplink budget. Then coming on to the next one, that is determine the transponder output power from its gain or output backoff. So we have to deal with the transponder output power. The output power of transponder gain directly depends on the amplification provided by the transponder. The next one is output backoff, which is used to reduce the distortion. So what is the output backoff is generally the satellite amplifiers are non-linear at higher power levels. This is called output back-off. To avoid distortion, the engineers reduce the operating power slightly. This reduction is called output back-off, which is very crucial in satellite design. In the step 6, we are going to establish the downlink power and noise budget for the receiving earth station. So these are very important based on the satellite ERP, based on the free space loss, based on the atmospheric loss, based on the rain attenuation, based on the earth station antenna gain, based on the receiver gain also. So in the step 7, we are going to calculate the C bar N, that is carrier to noise down power as well as carrier to noise up power at the worst case location that we are going to see. So this is depends on the footprint. So footprint is nothing but the coverage area, geographical coverage area of your satellite. So that depends on the only about the footprint only. Next step, we are going to calculate the SNR bar BER. So in the SNR, it is nothing but the signal to noise ratio. Each measures the signal quality or signal strength also we can say. Higher the SNR, better the communication. Similarly, the next important parameter is the bit error rate. So bit error rate is the measurement of transmission errors. It should be as minimum as possible. So the desired bit error rates are some typical values. For example, if it is voice, it should be 10 power minus 3. If it is data, it should be 10 power minus 6. Higher quality digital data may have 10 power minus. In the step 9, we are going to determine the link margin. Link margin is a safe reserve place that we can have. That safe reserve place should be maintained carefully. It is very important because it protects against rain, equipment aging, unexpected losses, as well as about the atmospheric variations also. In the step 10, we are comparing the results with the specifications. So in the step 11, we are going to have the peak system parameters to obtain the acceptable CNR, SNR as well as BER values. In the step 12, we are going to have the propagation condition determination we can say. That is, the propagation condition determination involves it about the rain statistics, atmospheric losses, and the seasonal variations, as well as about the geographical conditions. In the step 13, we are going to estimate the uplink and downlink unavailability. So no communication system is 100% at any time. So this gives the perfect condition for propagation. In the step 14, the redesign system by means of changing some parameters if the link margin are inadequate. So if the link margin, suppose required margin is 5 dB but the obtained margin is 2 dB, then we have to adequate the by means of designing the compensation. So this design inadequate can be compensated by means of using a larger antenna or higher transmitter power or better coding or by means of lower operating frequency. So ultimately we have to reach the required margin of 5 dB. By raising from the 2 dB to 5 dB we can able to achieve. So the evaluate practical feasibility was done in the step 15. If yes, the both counts in the step 15 and the satellite link listen is successful, so we can stop. Or else we can go from the step 1 and repeatedly again we have to do the same process steps. So this will give the successful design for a link design methodology. So the link design methodology and their interpretation is depicted in the diagram with the additional path loss values on the x-axis as well as the ground elevation angle that is on the y-axis. So the complete design cycle is given here. So the diagram depicts the link power budget and their interpretation very clearly. So this diagram shows the path loss due to the slant range versus the ground elevation angle. In the next slide, we are going to see about the various atmospheric effects on the link budget and their interpretation. As I already told you, the Faraday's rotation as well as the absorptions, so as well as the dispersions, what are the range of effects that is on the propagation effect based on the frequency that we are using. From the table we can clearly see for 100 megahertz, for 300 megahertz, for 1 gigahertz, for 3 gigahertz, for 10 gigahertz, we can have the various values. So these are the various atmospheric effects. As I already told you, the Faraday's rotation, time delay, refraction, dispersion also plays a crucial role in determining the characteristics of propagation as well as the link budget design. So the link budget design directly depends on the tropospheric gases also, since all of them absorbs the air, water, whatever it may be, it will absorb the microwave so that it will induce attenuation. So that's what the rain also plays a crucial role in the attenuation. So rainwater absorbs the microwave signals so that it will also cause the attenuation. So with that I am winding up my lecture. Thanking you one and all for hearing my lecture patiently. Thank you one and all.